radiation in magnetic field. So just the same rule, just remember for alpha, you will use the left, and for beta, you will use the right hand. And in both rules, your first finger or index finger will represent the magnetic field direction. Your second finger point towards the motion of the particle or the movement of the particle, initial movement of the particle. And your thumb will represent the force, the direction in which the particle experiences the force, that will, or the deflection, you can also say. So example, if it is cross, I'm just repeating the previous example. Cross means the magnetic field is pointing in. What is the meaning? Like north is outside the paper and south is inside the paper. So the magnetic field will point from north to south. And you have the alpha particle which is moving towards right hand side. So if alpha particle is moving towards right hand side and the magnetic field is into, so I will use my left hand. My first finger should point towards the south, which is into. My second finger point towards the direction, which is towards the right. And my thumb is pointing automatically the deflection. So the deflection will be upward. So when this alpha particle enter, it will go up. And opposite will be there for beta particles. If we have a deflection, or show the deflection of a beta particle, the direction, the cross means, the meaning of a cross means magnetic field is in, and meaning of a dot means the magnetic field is out. So for first, your first finger point towards the direction of the magnetic field. So if it is cross, your first finger should point into. If it is dot, your first finger should point out of the paper or towards you. Like if it is cross, my first finger should point into the paper or on the screen. And if it is dot, my first finger should point out of the paper or out of the screen or towards myself. If it is a beta particle, if it's a beta particle, the same, but instead of left, you will use a right hand. Your first finger should point towards south. So cross means into. My first finger should point into. But my second finger should point in the direction of beta. Beta is not moving towards left, it is moving towards right. So my second finger should point in the direction of the beta, which is towards right. Where my thumb is pointing downward. So if my thumb is pointing downward, when this beta particle enter, it will deflect or go down. Is it clear? The deflection of alpha and beta when magnetic field is into. But it can be other way around. The magnetic field can be out. Out means represented by the dots. Now we want to show the deflection of alpha and beta in the magnetic field. So example, alpha particle is entering and beta particle is entering. So if I want to show, if I want to represent for alpha, my first finger should point in the direction of the magnetic field. But in this case, because it is dot, if it is dot, so my first finger should point towards me. So my first finger is pointing towards me. My second finger is pointing. You're not able to see my first finger as it is pointing towards me. The second finger is pointing in the direction which the alpha particle is moving. Where my thumb is pointing downward. So which direction this alpha particle will move? It will go down. And for beta, I will use the right hand. My first finger should point in the direction of the direction in which the magnetic field. So it should point out. My second finger should point in the direction. So first finger is pointing in the direction of a magnetic field, which is out. Second finger is representing the direction in which the particle is moving. So which direction this particle is moving? It is moving towards right hand side. So it is moving towards right hand side. Where my thumb is pointing up. So this alpha beta particle will go up. And there's also a simple way. You can just remember if the magnetic field is same, if alpha particle is going down, beta particle will move up. And opposite, you can see if alpha particle was going up, beta particle will go down. So alpha and beta in the magnetic field are always moving opposite to the direction of each other in the magnetic field. Intensity of the curve, not about intensity, but the deflection of beta. When you represent, it's not like when you show a deflection, the deflection of the beta because of its small mass is more than alpha. Because alpha is having alpha is heavier, beta is lighter, so it can deflect easily in the magnetic field. So if I say I have a magnetic field which is cross, and both alpha and beta particles are entering the magnetic field from the same direction. A red arrow is representing alpha and a blue arrow is representing beta. And both enter the magnetic field from the same direction as same magnetic field. So alpha particle, which direction it will go? The alpha particles. So when I apply, first finger represent magnetic field, second represent direction, alpha should go up. So alpha particle should go up. I will show a deflection, but a small deflection, it will go up, but relatively small deflection. But if it is beta, beta will go down. And when I show a deflection, it should be a large deflection or a greater curvature. Is it clear? The deflection of alpha and beta in the magnetic field. The gamma is not deflected by magnetic field. Why? Because it does not have any charge. Only charged particle can be deflected in a magnetic field. If it is a dot, it means the magnetic field is out. If it is a cross, it means magnetic field is in. So cross means in and dot means out. So if it is cross, if alpha is moving up, beta will go down. If it is dot, alpha is going down, so beta will go up. So you can see when we change the direction of the magnetic field, the direction of the deflection will also change. Here in cross, alpha was going up, but in dot, alpha is going down. In cross, beta was going down, and in dot, the beta is going up. But you may have a magnet like north and south pole. So this is a north pole and this one is a south pole of a permanent magnet. An alpha particle is entering from left to right. So in this case, when we want to, for this part, we cannot draw the path exactly. We can just explain in words. So first finger, my first finger should point towards south because the magnetic field is always from north to south. So my first finger should point towards south. South is down. That's why my first finger is pointing down. My second finger should point in the direction which the particle is moving. So where my thumb is pointing, like my first finger is representing south, which is down. My second finger is representing the direction in which the alpha particle is moving. Where my thumb is pointing into the paper. So it means when this alpha particle will move, yeah, left hand, you have to use a left hand for alpha particle. First finger represents south, second represent direction of the particle, thumb is pointing into. So when you apply this rule, so in this case, what happened? Which is moving perpendicular to magnetic field. Perpendicular means 90 degree. You can see the magnetic field is pointing from north to south, and alpha particle is moving 90 or making angle 90 degree. So when the alpha particle which is moving perpendicular to the magnetic field experience the force into the paper and move in a curved path. So sometimes they say explain, they don't say draw, they mention explain the deflection of the particle in a magnetic field. So what are the points you will include? And this is a 3-mark question. So the points you will include that the particle that if it's an alpha particle, you'll say alpha particle. If it's a beta, you will say beta. So alpha particle, which is moving perpendicular to magnetic field, experience a force into the paper and move in a curved path. Because there are some questions in which they mention describe the motion of particle in a magnetic field. Same way, if you are having a beta particle, magnetic field poles are there, north and south, and beta particle is moving towards right. Apply the right hand rule, and which direction the beta particle will experience the force. Apply the right hand rule. First, your first finger, index finger should point towards south. Your second finger should point towards right hand side, and your thumb will point the direction. Your first finger should point towards south. So apply the right hand rule. Your first finger, my first finger should point towards south. My second finger should point in the direction where the beta is moving. Where my thumb is pointing, my thumb, it's pointing out of the paper. It's not up. This is called up. This is out of the paper. So in this case, the thumb is pointing outwards. So if it is pointing towards you, you will say out of the paper. If it is pointing towards the paper, you will say into the paper. So how we describe this path? So it's the same thing, but only change what I will make. in this case, I don't have alpha particle. This is a beta particle moving perpendicular to magnetic force, field, experience the force out of the paper and move in a curved path. Is it clear? The deflection of these particles in a magnetic field. Any doubt in this? Now, what is the background radiation? Background radiations are radiations from the surrounding. Other than source. So radiations from surrounding other than the source are refers to background radiation. Example, you have a radioactive source. It is emitting out radiations. And you place a detector, the GM tube. Just you should know the name of the detector. That's called a Geiger-Müller tube, or you can, in short, you can say a GM tube. It's a cylindrical tube. So a GM tube example record 200 radiations when it is placed in front of the source. But if I remove the source, there is no source. And I place the detector in the room where I don't have any radioactive source. What should be the reading on the GM tube? It should be 0, but practically it will not be 0. Why it will not be 0? Because in our atmosphere, in our surrounding, there are also radiations from the source. There are also radiations, and these radiations, which are not coming from the source, but they are coming from the surrounding, these radiations are known as background radiations. So radiations which are not coming from the source, they're actually from the surrounding. And what are the sources of background radiation? What is the origin of the background radiation? Origin or the sources of these background radiation? There are different, like we have a radon gas in our atmosphere. Radon is also a radioactive. Radon also emit out radiations. So even inside the ground, we have some radioactive materials. So it can be from ground. It can be from outer space. Like there may be a radioactive particles which are radioactive material which are emitting out radiation. So that is coming from the space and our detector may record those. Maybe nearby a power station is there. Even in medical field, we are using for treatment of the cancer, we are using cobalt, which is also a radioactive. So maybe nearby medical facility or hospital is there which is treating a cancer, so that is also emitting out radiation. So a detector may record those radiation. A radon gas is there which is present in the atmosphere, that can also be detected. Maybe A power station is there, nearby power station. So nuclear power station. So what happened in reality, it will not record the actual. So example 25, normally 25 to 50 radiations are coming from the background. So if I want to find the radiation, actual radiation from the source, so what is the formula? If I want the radiation from the source, that is reading with source minus reading without source. Reading of the detector basically. So example, first what I will do, I will have a radioactive source and I place a detector in front of this and I record the radiation. So radiations are coming out 370. Then I remove the source, I just place the detector and record the radiations again. It is coming out 30. The question is, how many radiations are from the source? How many radiations are actually from the source? So that's equal to 340 because this one is actually a sum of source. It is recording a radiation from source and it is recording a background. This one is only background. So if I subtract the total reading minus the background reading, so I'll get the radiation from the source. So in this case, the 370 is the total reading minus the background. So that is equals to 340, which are actually from the source. Is it clear the concept of the background radiation? Because in our atmosphere, there are different radiations. Our eyes only can detect the visible range, which is from 400 nanometer to 700 nanometer. Radiations above or below this are not able to, or our eyes not able to detect. And so these radiations are present in the atmosphere but not visible to us because our eye is not sensitive. So detector such as a GM tube can detect those radiation and which are from the surrounding. We call them as background radiation, and the reading which we get from this is known as the background counts. Then what is the half-life? It is time taken by half of radioactive sample to be stable. So how much time the half of the radioactive sample will take to be stable, we call that as a half-life. Example, you have 100 gram of a sample which is unstable. Unstable means it is emitting out radiation. It is radioactive. What is half of 100? That's equal to 50. So basically what happened in the beginning, you have 100 grams of radioactive material, or I am writing unstable material, means emitting out radiation. You will have, after some time, you're left with or time taken by this total 100 gram to become 50 gram stable and 50 gram still unstable. Like 50 gram stable means 50 gram is not emitting out radiation, and still unstable, 50 gram unstable means still emitting out radiation. So this time it will take to change half of its original value to be stable, that time interval is known as half life. So from the name you can understand half, and life here refers to time. So half time or half life. Example, if this 100 gram changed to 50 gram stable and 50 gram unstable in 4 days, what is the half life? So what is the half life of this sample? The 100 gram is changing into 50 gram stable and 50 gram unstable. What is the half life of this sample? Half life is also 4 days, because half life is the time taken by the sample to be half of its original value. Like example, 100, originally 100 gram is stable, sorry, unstable. Then after 4 days, you're left with 50 grams stable and 50 grams unstable. So half of 100 is equals to 50. So when compared to original value, when you're left with half of the unstable sample, you call that time interval as half-life. Same thing, if I say half-life of this sample is 4 days. If half-life is 4 days, you're left with 50 gram unstable. So this 50 gram unstable will also break down or decay. What is half of 50? That will be 25. So means you will have 25 gram stable and 25 grams unstable. So if the half-life of the sample is 4 days, every time when it will change half of its original value, it will always take 4 days to complete that. So if 100 change to 50 in 4 days, the 50 will change into 25 also in 4 days. So half-life does not depend on amount of the material. It only depends on the type or the element which you are using. Whether the element is very unstable or it is stable. So it depends on the stability or instability of the element. Some elements have a longer half-life. For example, some elements have a half-life about 4,800 years. That's a too big time interval for the sample to decay. And some elements have a very short half-life, like example, 8 minutes. So within 8 minutes, they decay or break down into half of their original value. So example, if I have the half-life of the sample three days, find amount of sample which is stable and unstable after 12 days or after 9 days if original unstable sample is 200 gram. So half-life of the sample is 3 days, means that after every 3 days, it will turn half of its original value. Find amount of sample which is stable and unstable after 9 days if original unstable sample is 200 grams. So originally we have 200 gram, which is unstable. After 3 days, because after every 3 days, it will be half of its original value. So after 3 days, how much will be stable and how much is unstable? 100 gram will be stable and 100 gram will be unstable. But we have to find time, like total after 9 days, how much it is stable and how much it is unstable. So a stable one will not decay, but unstable one will further decay. And unstable one will further decay. What is half of 100? That's equal to 50. So after, and how many days after further 3 days? Because after every 3 days, it will be half of its original value. So this will be 50 grams stable and 50 gram unstable. Then, but we have to find after total 9 days. So 3 plus 3, it makes 6 days. So further, if it further decay, after further 3 days, that will make the total interval 9. So it will be 25 gram stable and 25 gram unstable. So that will make the total interval that makes the total interval 9 days. So after 9 days, how much of the sample after total 9 days, how much of the sample is unstable and how much of the sample is stable? What is the amount of sample stable after 9 days? Oh, sorry, unstable first. What's the amount of sample which is unstable or still emitting out radiation after 9 days? So after 9 days, 25 gram is still emitting out radiation. So unstable is 25 and originally it was 200. So stable will be 175. Is it clear? You can add these number 100 plus 50 plus 25. That will make 175. So for half-life questions, you don't have to use any formula. You just have to use your understanding of the concept and solve a question related to the half-life. You don't have to use any formula for half-life, just the simple division method that after every half-life, the sample will be half of its original value. Is it clear, this example? So originally we were having 200 gram of the sample with a half-life of 3 days. So means after every 3 days, this will become half of its original value. Like half will be stable, half will be unstable. So half of 200 is 100. The 100 will be stable and 100 will be unstable. Then the 100 which is unstable will not stop. It will also decay. And after 3 days, it will become half of its original value. So it will become 50 grams stable and 50 gram unstable. Then after further 3 days, the 50 gram which is unstable will decay into 25 gram stable and 25 gram unstable. So after total interval of 9 days, we are left with 25 gram unstable and we are left with 175 gram stable. They can also ask this question in terms of atoms. Like if I say 100 radioactive atoms, with half-life 4 days, find number of stable and unstable after 8 days. So originally you have 100 radioactive atoms. So originally I have 100. So after 4 days, because I want the total time interval to be 8 and the half-life is 4 days. So after 4 days, 50 will be stable and 50 will be unstable, still emitting out radiation. Then after further 4 days, 25 will be stable and 25 will be unstable. So total interval means 8 days. So after 8 days, how many are stable atoms and how many are unstable? So 75 are stable. So 75 of them gain stability, so they're stable, and 25 of them are still unstable or still they are emitting out radiation. Is it clear, the concept of the half-life? So next class, we will discuss more questions related to the half-life. This is one type of question. There is another type of half-life question which include the background radiation, like in which the question include or having a background radiation as well. That's only one more step is there for that type of question. So next session, I will discuss the half-life question with the background radiation. And next week, we will complete this block 5. Regarding the model of atom, yes, the Rutherford experiment is there, so that we will discuss. The things which are left, half-life questions practice, Rutherford experiment, and the nuclear reactions such as fission and fusion. So I'll end the session and share the recording.